Hello everyone, this is Shuaishuai, a PhD student from Professor Bevan's group at McGill University. Today, I'm going to talk about atomic insight into the lattice dynamics driving the relaxation of charge defects. Electronically driven lattice rearrangements are often shown in many ionic or oxide materials. For example, when an electron is removed from a single side, we can see it drives the spontaneous lattice rearrangements. This charge-induced lattice rearrangement is closely related to many phenomena, such as the change of charge state of point defects, electron or hole transfer, optical excitation, and small polaron formation. These phenomena are shown in various technologies, including solar cells, batteries, and photoelectrochemical cells. Further atomistic understanding of such process can significantly aid the design of many energy materials, and this is the focus and motivation of our research. In this study, we use sodium chloride F-center as our model system. Here, red dots represent sodium ions and blue dots represent chloride ions. Sodium chloride F-center is just an electron localized in a chloride vacancy. We can see there is almost no distortion near the F-center. But once the trapped electron is removed from the F-center, it becomes a charged F-center, and the surrounding lattice got to relax. In this presentation, our focus is on the lattice dynamics through the charged F-center formation in sodium chloride. In the process A to B, we could see that the total energy drops down, accompanied by lattice relaxation. About this lattice relaxation process, there are a few questions that we would like to answer. How does the excess energy dissipate during this transition process? Which phonon modes dominate the dissipation process? How long does it take to relax the lattice? How do these characteristics vary as a function of temperature? We choose sodium chloride F-center as our model system because this can be studied by classical molecular dynamics, which make it possible to test within large supercells in time ranges. This is very important since the supercell size has to be large enough to observe the realistic energy dissipation process in a realistic timescale. With this simple system, we hope to clearly show the whole process of lattice relaxation after the removal of a localized electron and the challenges posed by such calculations, which may enable first principles method to study the formation of charge defect centers or small polarons. Let's first look at results from some static calculations before delving into the molecular dynamics. We want to first see the lattice distortions between the initial configuration A and final configuration B. We can visualize the distortions between the initial and final configurations by plotting the atomic relaxations as a function of shell index from the defect side. From the plots, the first two shells have most distinguished distortions, with 6 sodium ions moving away from the vacancy and 12 chloride ions moving towards the vacancy, and the displacement could go beyond 20 shells near the vacancy side. Here, the changes of the initial and final states are shown in the real space. There is another way to show the distortion field. We could also project the total distortions onto the phonon space coordinates of the configuration B. Here we have a 6x6x6 supercell with about 1700 atoms. We could see that the phonon modes decomposition of the total distortions gave similar magnitudes at all frequencies. Many phonon modes got excited, while the mode with higher frequencies get more potential energy, also because of the omega square in the potential energy terms. There's a clear dominance of the high-frequency optical modes. The 3 optical modes take up more than 50% of the total energy. These 3 modes are high-frequency stretching mode. For example, the visualization of 9.1 THz mode is shown here, with sodium and chloride ions having opposing motions. All the ions point towards or out of the defect. With the analysis of the distortion field, let's proceed to the molecular dynamical part. The molecular dynamics calculations are separated into 4 stages. The first 3 stages are used to prepare the system to a target lattice temperature. I will skip the details in this talk, but the goal for these 3 stages is to carefully prepare the system, have randomized phases and phonon energies, and smaller temperature fluctuations and noise. Generally speaking, the number of MD samples are increasing with target temperature. In the final 4th stage, a chloride ion was removed to mimic the formation of an F+ center due to the electron ejection from the F center. The dynamics of relaxation from configuration A to configuration B were then tracked both in real space and phonon space within stage 4. With the displacement and velocities, now we can start analyzing the MD results. The first analysis is in real space. We could calculate the local temperature near the defect during the dynamical process. The blue curves are local temperature versus time in the 10 shells of atoms that are closest to the chloride defect, highlighted here. And the temperature fluctuations are fitted with an exponential decay. This image is when the perturbation takes place under 50 K. As the temperature of the thermalization stages changes from 25 K to 300 K, we could see that the decay time constants are about the same, so the decay time has weak temperature dependency. We then apply the normal mode decomposition approach, have the analysis in phonon space. The atomic trajectories and velocities during each step of the molecular dynamics can be projected onto the phonon mode coordinates of the systems, and then the energies of each normal mode can be calculated. Let's first look at the case of 50 K. We notice that there are still the 3 high-frequency modes that dominate the dissipation of the excess energy. If we vary the thermalization temperatures, we could see that it is completely different from the local temperature fluctuations. Here, the energy decay of the 9.1 THz mode shows a strong temperature dependency. And compared with the local temperature decay at the vicinity of the defect, some phonon modes take much longer to dissipate their energy. Another way to visualize the result in the phonon space is to track the redistribution of energy amongst all phonon modes in the 2D heat map. The x-axis is still time, and the y-axis is the frequency of the phonon modes, and the color represents the energetic phonon densive states that we defined, where ES is this energy of the phonon mode S, DS is a Gaussian, and the integral of the upsilon gives the total energy. We plot the upsilon deviation respect to the equilibrium value as the state B, and during the transition between A and B, the excess potential energy at the initial configuration A is redistributed and reached to the steady state B. And with this plot, now we can more clearly see the energy redistribution with respect not only to time, but also to frequencies. We can see that the energy at higher frequency is decreased, or we could see that the phonons are depopulated. At lower frequency, we can see that the energy is increased, or we could see that the phonons below 6 THz are populated. Here are the phonon population changes at various temperatures from 25 K to 300 K. Despite the decay lifetimes are different, the overall decay trend, the pattern, is very consistent. How about we further assume that all modes work in concert to dissipate this excess energy at the start point A as a first-order exponential decay process? We already know that the potential change, the delta US, in the static calculation of the potential change between A and B, and we also have the lifetime of the phonon mode of 9.1 THz. What if we just make a rough approximation and assume all the modes have similar lifetimes and have a first-order exponential decay process? So we plot this in analytical form, and we find that this phenomenological model captures many of the physical trends present in the MD simulations. We can view these phonons just as particles, and during the transition between A and B, the excess potential energy is subsequently transformed into thermal energy through redistribution among all the phonon modes. This phenomenological model arises from treating the dissipation physics acting on each phonon mode via Langevin dynamics. Though we caution that this agreement is likely an averaging or aggregation effect, as such individual phonon lifetimes are expected to vary above this mean, and we can see that the long time scale annihilation process below 60 terahertz is excluded in this analytical model. Let's end with the picture we start with. How does the energy release when forming a charge defect? We could see that the formation time is still quite an ambiguous concept. There are at least two ways of defining this decay time or relaxation time after perturbation. One way is based on the changes of local temperature, and another way is based on the changes of phonon mode. For the phonon mode, it has a much stronger temperature dependency, and at low temperature, it has longer lifetime. Whereas for the local temperature, it has a relatively weak temperature dependency, and it has slightly shorter lifetime at low temperature. And this can be connected through the common theme of phonon dynamics. At lower temperature, phonon scattering is reduced, leading to a longer phonon mean-free path, thereby longer phonon lifetimes. A longer phonon mean-free path also leads to more rapid dissipation of thermal energy around the defect center, thereby faster decay for the local temperature. The missing piece of the puzzle is how do we develop a quantum model that captures the temperature-dependent phonon decay trend? This involves calculating phonon lifetimes through the atomistic investigation of the higher order and harmonic coupling terms and the inclusion of quantum effects. That's the end of my talk today, and you may also refer to our paper to have more information about it. Thank you. Thanks for your attention.